Welcome back, everyone, to the Compton lecture series. This is the sixth lecture. I recognize most of the people here, so I won't belabor the introduction. My name is Wyman. I'm a postdoctoral researcher here at the university. And today we're going to be finishing our finishing not the lecture series, but our story of the universe by talking about the dark energy crisis. And so this will be the last week that we return to our now familiar timeline of the universe that I've been starting each of the lectures with. And so we started way over here on the left with the inflationary epoch. And so today we're going to talk about what's going on now with space. By now I mean not the formation of structure, which is more or less been turned off, in fact, at the present moment. But to talk about what's going on with the universe today and going into the future. And what is going on with the universe today? Well, this year's Nobel Prize in Physics was awarded to these three astronomers, Paul Perlmutter, Brian Schmidt, and Adam Rees, for their discovery of the accelerating expansion of the universe today, and for about the last billion years or so. Billion would be. And at least, well, maybe even longer than that. But that was about, anyway, I should know that number. But so not only is it timely from the cosmological sense of learning about what our universe is doing these days, but it's also timely from a cultural sense of this, the sort of most distinguished body for recognizing scientific advances has elected this year to bestow this Nobel Prize on this particular subject. And so even though I'm not, obviously, one of these distinguished gentlemen, I'll do my best to explain why it is that their discovery merits this great honor. So, what is this dark energy that I'm telling you is a crisis? So, I've described this before, but let me just run through it again. And basically, the discovery is the universe is right now increasing its expansion rate, so that if you went back 500 million years and you measured how fast galaxies are moving away from each other, and compared that with how fast galaxies are moving away from each other today, then that velocity has increased in time rather than decreased. And so Einstein's equations tell us that no ordinary form of matter or energy density can cause expansion rates to increase in time. All of them cause expansion rates to decrease in time. And I'm not going to go into this in a great deal of detail today, because this is exactly the same phenomenon that we discussed in the second lecture on the inflationary period. And so it's a very similar physical phenomenon where the universe's expansion rate is increasing in time. And for that to happen, you have to have a material or substance or phenomenon that has an effective pressure, or what in normal matter looks like pressure, that is in fact negative, which is weird, and also equal to the energy density, the energy density itself. And those words don't mean a lot in this context. But what it basically is a substance that causes gravity to switch its sign, to push out rather than pull together. And so the intuition you have is that whenever you have a universe filled with ordinary matter, then as time goes on, it slows down because the gravitational force of all the stuff in the universe is pulling on all the other stuff and slowing down that expansion. And so, in the same way that we don't know of anything on Earth that gets pushed up by the gravitational field of the Earth, so also do we not know of any substance that does this on the cosmological scale. Because if you could localize such a substance, if you could make a ball of dark energy, then you would indeed see that it would have very bizarre properties. Though I don't think that it's hard to think through exactly how this would work if you try to put it in the equations. But how a ball of dark energy would behave close to the Earth is hard to picture, because part of its essence is that it's something that is diffuse in the background of space. And so the reason I have a picture of Einstein here is not only because Yes, ma'am.
I'm wondering something, if there's galaxies, I mean, the pressure of dark matter is apparently causing the expansion, but within the galaxy we don't expand. Does that mean there isn't any dark matter?
Okay, this is a point I wanted to make. So, it's in an eagerness for advertising potency that is so characteristic of our times, cosmologists have named dark matter and dark energy both with the epithet dark, because dark sounds cool and exciting. But dark matter and dark energy, in fact, we think have nothing to do with each other, other than we both call them both dark. We call them both dark because we don't know what they are. And we don't know matter, and we have no idea energy isn't quite as pithy as dark matter and dark energy. And so we know dark matter is in fact pressureless. Its pressure is zero. But it has nothing to do with the dark energy, which is diffused through space, which has this negative pressure property. Does that answer your question? Okay, well, so we have dark matter, which is in the galaxy, which we had last lecture was about. And so that's some substance we don't understand, but it acts like matter. It has a mass, it has a weight. It can be localized. You could make a ball of dark matter. It wouldn't hold together, but you could make it. Dark energy, on the other hand, is some other substance that is not at all like matter. It's very bizarre. It's much more bizarre than anything that you can possibly imagine.
Trying to make a distinction between why we don't expand within the galaxy.
Right. So, and so this is another fine point. And so actually, let me just spend 1 minute addressing it, because this is a point that causes many people a lot of confusion. And so, her question is essentially, how is it that basically is the expansion? If I may guess, what you mean is why is the Earth not being pulled away from the sun in the same way that galaxies are moving apart from each other? And the answer to that is the real answer is the disappointing one that if you understand, when you study the full set of equations, and that's just what you find, the intuitive answer goes something like this: that the expansion rate, the relative expansion of things that comes after the Big Bang is in some sense just remaining momentum. It's just the galaxies have always been moving apart, and so as long as nothing keeps them from moving apart, they keep moving away from each other. And so, but the sun and the Earth, or our galaxy, or our sun in the galaxy, have something that's holding them together. That is the gravitational force, and that's far strong. So that compelling force has stopped them from this overall expansion. It's just a remnant from that early universe expansion. And so that picture is almost exactly correct, and you get 95% of the right answers by saying that. The problem is that if you keep cranking up the expansion rate higher and higher, then eventually you get to a place where actually the background does start kicking in even between the Earth and the Sun, or in galaxies. And if you make that expansion rate really high, then you can in fact pull the solar system apart. And so, but that would be an expansion rate much more characteristic of the inflationary period, which is to say many orders of magnitude larger than our current expansion rate. And so, to understand the expansion as we see it today, you can basically assume the expansion rate is so weak that it's easy for gravity to beat it entirely, locally. But I don't want you to have the takeaway that that's the whole story, because the whole story is just complicated. And that's why we have to it takes us about 10 years of constant study to be able to solve these equations consistently and understand what's going on. So, I'm not saying that to discourage you, but just to say that if you don't get it, you're not alone, and it really is hard. Okay, so I'm really glad you asked that question, because it's one of the key conceptual questions of cosmology, and it's very hard to get your wrap around the right answer. And in fact, a friend of mine at NYU, whose name is David Hogg, he's a really great guy. He's an astronomer. He and a couple of people have been writing papers against each other arguing about the best way to explain this point to students, where he said, well, I think that you should explain it this way, and these other people said it's wrong. And so even among experts, we have arguments about the best way to articulate these facts, because we all agree on the answer from the equations. But to dissect that into a language that we can, even among ourselves, agree on is very difficult. And so if you're struggling with it, you are not alone. I want to hold, unless it's really critical, I want to hold the rest of the questions for now. Okay, so, is it really critical? And then another major point of conceptual. Okay, so, why do I bring up Einstein when I talk about dark energy? Well, so, in Einstein's day, before the discovery of general relativity, the popular view among smart, educated, sophisticated people was that the universe was always the same, and that the universe in the distant past is the same as the universe now, and the universe now is the same as it will be in the distant future. And this was later sort of called a steady state universe. But whenever people started looking at Einstein's equations, they did not admit solution. The equations as originally written did not allow stationary solutions. They only allowed expanding and contracting solutions. And this is what was discovered by George Lemaitre and Friedman, Walkerson, and Walker in the early these early general relativists. And Einstein was, even though extremely brilliant physicist, on this one kind of, he reacted with the prejudices of his time and said, well, man, my theory is wrong because, the universe is obviously staying stationary. So let me just change the theory to make the universe stay still. And so he put in a new term in the equation, which he called the cosmological constant term. And basically this term was just, you say, okay, the universe is contracting, and put in a form that exactly balances out that contraction, so it just stays still. And so it's a term that would push out, versus relative to the tendency of the universe to fall in. Or if you would flip the sign, if you had a universe that was expanding, it would be a term that would keep the universe from expanding. So it turned out that, obviously, very soon after he did this, Edwin Hubble proved observationally that the universe was, in fact, expanding. And Einstein called this his greatest blunder. But even the blunders of geniuses turn out to be useful. And so a term of exactly the same form, though of a very different size, is in fact the best way to describe this, the simplest way of describing this accelerated expansion now. In contrast to what Einstein wanted to use it for, we aren't using it to keep the universe steady, but we use it to describe the fact that the universe's expansion rate is increasing in time. So I just wanted to remind you of this slide from the very first talk. And so what does dark energy do? And so if you just look at a smooth patch of space, and don't confuse yourself thinking about galaxies or anything, then you talk about how the radius of that patch changes in time. And then this plot shows you the three different ways that radius can change. So you have normal cosmologies, so cosmologies that are just filled with ordinary matter or radiation. And so they increase sort of slowly, and so they're just slowly increasing in size. And you had a constant rate of expansion, just plugging away, never slowing down. You have this blue line. And so what dark energy does is the same thing that inflation does. Is that the rate of expansion is actually increasing in time. So the longer you wait, the faster you go. And so because it's a constant acceleration, not a constant velocity. And so one of the things I wanted to spend, and this is why I belabored the nice point that was raised. So one of the things I wanted to spend some time on today was talking about what this expansion of space, some of the consequences of this expansion of space, because we've made it through 5 lectures on cosmology without talking about this much, and yet it's one of the fundamental, the key facts about the universe that we know. And so I'm just going to imagine a triangular piece of space, and so I've projected out, I'm only writing 2 dimensions because I don't have a 3-dimensional projector. And so this triangle, I've doubled in each dimension. So this triangle right here has doubled the area of this triangle. And so if you imagine that this was some volume, it would be 8 times the volume of the original triangle, okay? And so this expansion of space in a flat space doesn't deform anything, so shapes are preserved. And so they just get bigger. So now imagine that this triangle was filled with ordinary matter, or dark matter. So in such a space, in such a volume, matter density is, matter is conserved. So you have a certain number of dark matter particles, say, or a certain, 18 basketballs. It all works the same. And so if you make the volume of this patch of space 8 times bigger, then the density of the matter in that volume goes down like 1/8, right? So that's just like in ordinary physics. And so that's how matter dilutes as the universe expands. And because one of the facts about Einstein's equations is that Einstein's equations are local equations. All of the known physics equations we have are what we call local equations. And that is that their solutions depend only on the value of the facts that you can know in a little tiny patch around where you are. And so you can't measure the total mass of the universe locally. There's no way I can right here measure the whole mass of the universe. But I do know what the density of stuff is right here. And so the equations only, the solutions of the equations depend on the density of the stuff in the universe, not on the total amount. And so that's why we have to know how the density changes in time if we want to solve the equations in time. And so matter is easy. So radiation, however, is a little bit weird. And so radiation, if you have a box filled with radiation, then you have you can just imagine that you have a certain number of photons. And so if you double the size of that box in every dimension, the volume goes down by a factor of 8. And so you might think that the density of the radiation, particles also decreases by a factor of 8. But space itself is expanding too. And remember that the energy in any particular photon is correlated to its wavelength. And so if you have longer wavelengths, then you have less energy. And so that's a 1-to-1 relationship. And so if you double the size of a box, then you half the wavelength of each of the photons in that box. Because photons are stretched by the expansion of space.
Double the wavelength.
So what?
Double.
Double. Did I say something else? I said half. Oh, double. Yes, thank you. You double the wavelength. Double the volume, double the size, double the wavelength. So 8 times the volume, double the wavelength equals 1/16 the energy in radiation. And so radiation gets diluted faster than matter. And so if you think about that backwards, then if you start today and go backwards in time, then that means that the relative amount of radiation increases relative to matter going backwards. And going forward in time, then the relative amount of matter increases faster than radiation. And so I'm going to illustrate that in one more slide. But I wanted to say, so the dark energy, whatever it is, this cosmological constant, the reason why it's called a constant is that you double the volume, you octuple the volume, and the energy density stays the same. So if you tried to add up, if you wanted to add up the total energy in this form increases by a factor of 8 during the expansion. So if that sounds weird to you, I agree. Nonetheless, it seems to be what's happening. And so this is something with a density that doesn't change. It does not dilute. So if you expand it, if you have 18 basketballs and you make a bigger box, you still have 18 basketballs. And if you make a bigger box of dark energy, you get more dark energy. So it's very strange. And so what does that mean? And so if you just imagine now just a square of space, and so again I'm suppressing the third dimension, but this is supposed to be a volume. And so imagine in that chunk of space that 25% of the density is in matter, that's blue, and 75% of the energy is in radiation. And so now I multiply each of the dimensions by a factor of 2, so it gets to be 8 times the size. And what happens is then, after it's increased, doubled in size in each dimension, then 40% of the density is now in matter, and 60% is in radiation. Because the radiation has been diluting faster than the matter. And so if you do that again, you go from 40 to 56% matter, and 44% radiation. And so you see that as time goes on, radiation plays a smaller and smaller role in the expansion of space. Now, if you do the same thing with matter versus dark energy, you get a very different story. Because dark energy is not diluted. And And so you can start with a small amount of dark energy, and in just 2 doubling times, you go from 25% to 96%. And so it turns out that, and I didn't even do this on purpose, but I should have, that 72% is about exactly how much dark energy, what fraction of the density of energy in space is present in dark energy today. And so you can then just use this figure to go back. So when the universe is half its present size, or 1/8 its present volume, then the universe is 25% dark energy. And if you go backwards from that, when it was 1/4 its present size, then the dark energy was completely negligible fraction of this. It was really, really tiny, a percent or so. And so dark energy, the nature of dark energy is it has a really, really tiny constant density. And so for most of the history of the universe, you can ignore it. And then suddenly, whenever the matter gets to be the same density as the dark energy, then the dark energy rapidly, over the course of a couple of doublings, takes over the story because it's not diluting. Okay, so how do we know this? How do we know all these crazy things I'm telling you? So what are these observations that got these people the Nobel Prize? So the first one is I want to remind you is that the fundamental clock that we use in astronomy is redshift. And redshift is what Edwin Hubble used to discover the expansion of space initially. And redshift is, if you may recall from chemistry class, that you have this Balmer series, or this series of characteristic energies that a hydrogen atom would emit. So different characteristic frequencies that a hydrogen atom would emit. And if you've seen, people may know sodium lights, like sometimes you have sodium lights on in the highway. They have a different color light from an incandescent bulb. So, and neon lights also, if we didn't, so neon lights also have a particular color, right? You all know this. And so all of the different gases, all of the different materials that we have characteristic spectra, particular wavelengths that match the structure of their electron energy levels. And these electrons, and so this particular structure is sort of a fingerprint, or something that we can use to identify each atom as being distinct. And so what we can see is if we see a particular pattern of lines, or a particular pattern of absorptions, if we have a continuous source in the background, then we can say, that light went through hydrogen, or that light went through sodium, or that light hit what came from the iron, or whatever. And so the way that we know that the universe is, one of the chief ways we know the universe is expanding is that we can see stars that are very distant. And we can see iron lines or hydrogen lines, but they're not at the right place. So a hydrogen line that we know is yellow on Earth, we can tell is becoming orange in some other galaxy. In some other galaxy, it's red. In some other galaxy, it's in the infrared. And so we can use this to figure out how the relative size of the universe when each of these bits of light were emitted, because they've been stretched in the intervening time to be in the relative to the values we measure on Earth in the wrong spot. So that gives us a time. So that means that whenever we observe something in the universe, we know when it happened, in the terms of how big the universe was. But to understand about expansion rates, to study to find out velocities, you know that we don't have time. Measuring time isn't enough. You also need a distance, an actual meter stick distance between two points. So then if you can compare how long ago something was versus how far away it is, then you have a series of those observations, and you can infer the velocity over time. And so there's two ways to do this in astronomy. One is if you have something of intrinsic brightness that you know, so like a 100-watt bulb. We know how bright a 100-watt bulb is. And so if you see the light, a bit of light, and you know it's from a 100-watt bulb, you can say, well, that 100-watt bulb, it seems is the brightness as I see it is, whatever, reduced by a factor of 100. And that means that it's 10 meters away, because the distance, so you can use the fact that we can measure the relative brightness, the apparent brightness of that known brightness object to figure out the distance between us. The other way of doing this is something called that's called a standard candle. So something that we know the intrinsic brightness of, and we can use that knowledge about the intrinsic brightness to figure out the absolute distance. The other thing we could do is something called a standard ruler, where you know the intrinsic size of something. Like if I held a meter stick up, then you could, if you all whipped out your calculators and used some a device to measure the apparent size of that meter stick, then you can figure out how far away I'm standing from you by looking at the relative angle of that meter stick. And so the smaller the meter stick appears, the farther away I am. And so we use both of these in cosmology. We talked about this one in the CMB, because the CMB provides us with a standard ruler. But in between the CMB and us, it turns out that the one we want to use is standard candles. And so one of the great searches of cosmology, of astronomy in the latter half of the 20th century, was for standard candles. Now, the first known standard candle was the one that Hubble used, which is something called a Cepheid variable star. And I don't want to spend too much time talking about that, but they're basically stars that pulsate, and their brightness is correlated with how fast they pulsate. And so if you can measure how fast they're pulsating, then you can figure out how intrinsically bright they are. And Cepheids are great. They're just not bright enough you can see them in nearby galaxies, but not in very, very distant galaxies. And so you can't use them for cosmology. And so to do cosmology, you need something that's really bright. And so if you want something that's bright, if you're an astronomer, your thoughts turn to supernovae. Supernovae are exploding stars. So stars that have reached the end of their life, whatever that life was, and then through some cataclysmic reaction, explode. So they take a great deal of their binding energy and trade it for explosive energy and light. And because this explosion is so violent, the light is bright enough to be seen over very, very great distances. And so there are many different kinds of supernovae, as there are many different kinds of stars that come before supernovae. But the ones that turn out to be the ones that are relevant for cosmology are ones that are called supernovae type 1a. And so type 1a supernovae are the one we're focused on. The rest of the supernovae are generally called type 2. And it turns out type 2 supernovae are ones that come from very big stars. And they're cool, but have all kinds of different brightnesses. The type 1a supernovae turn out to be our standard candles. It's a slightly interesting story. But I should just say, this is a picture that you have on the handouts of an actual supernovae that was observed in historical times, in 1572, by Tycho Brahe. And so we can now look at the same supernova that Brahe saw in 1572, and it's been, almost 400 years. Almost 100 years, 450 years. And so it used to be a really tiny point, but now it's turned into this big gas cloud. And so it's really cool. So we can actually learn a lot about supernovae by looking at these gas nebulae that are associated with historical supernovae. And so this one and another one that happened about 30 years later, you'll see by Kepler, are the last two supernovae we know of that went off in our own galaxy. And so it'll be really exciting to see one go off in our own galaxy now. The average rate of supernovae going off in galaxies is about 1 per century per galaxy. And so we're due. And so, if it happened, everyone would be very excited. And so what are these supernovae? So I said that the type 2 supernovae, excuse me, I'm getting over a cold, so I apologize if I occasionally pause to catch my breath. So type 1a supernovae, or as we designate them sometimes compactly, SNE1a, E for plural, SN for supernovae, 1a for type. They're former white dwarfs, and since we have pictures of white dwarfs, I thought I'd show you what one looks like. And so that little blob right there is a white dwarf. This is something that's not a white dwarf; it's a much brighter object. So white dwarfs, we can see they're very dim. They're very dim stars, and they're stars that are not undergoing nuclear reactions. So our sun is powered by nuclear reactions going on at its core. And it's taking lower elements and building them into higher elements, and using that fusion energy to generate the light energy that we all rely on. But white dwarfs are different. So they're assembled in a variety of ways. We're not sure which was the main one, but they're basically stars that are just big hot balls of gas that are just slowly contracting under their own gravity. There's no nuclear reactions going on. They're typically, a lot of them are former stars, so they're stars that already, that had nuclear reactions in the past that stopped for various reasons, sometimes. Anyway, so they're just a big ball of hot gas. And as time goes on, then those balls of hot gas get to the white dwarf stage where they're small enough that they're really bright and white in their emission. And so then they're bright and white in their emission, but they're really, really compact. This is why they're called dwarfs. So a white dwarf weighs about the same as our sun, but it's many, many times smaller than our sun in size. And so what's going on in white dwarf? So in a white dwarf, what you have is a situation where the gravity has slowly contracted the gas cloud more and more to the point where the fact that atoms have a finite size is starting to really, really make a difference. So again, I briefly mentioned this electron energy level story earlier. So again, dredge up those memories maybe from a previous Compton lecture, maybe from when you were in high school chemistry, maybe from when you were teaching high school chemistry. There's some teachers here. And remember that the structure of an atom is that, maybe I'll just draw this real quick. I'll take advantage of the chalkboard or not. Okay. Our picture is that we have a nucleus in the center, and then these energy levels around the nucleus where the electrons live, right? And so you can think of there being, one of the laws you learned is that in each energy level, there can only be 2 electrons, because electrons have spin. You only have one spin up and one spin down in each level, right? And so these levels have something like a finite size. And so usually this is fine. So in ordinary matter, these energy levels are, so ordinary chemical bonding happens whenever you have sort of the outermost energy levels of these electrons hitching onto each other, right? And so they end up sharing electrons. And so what happens in a white dwarf, though, is, so an ordinary bond would be another atom over here, and so it's overlapping here, and so these 2 atoms are sharing one of their electrons, right? So what happens in a supernova, this is a very, very stable situation. So these are the fundamental bonds that make all of including the most dense pieces of matter that we know about. So what happens in a supernova, though, or in a supernova, yes, but in a white dwarf, is that the gravitational force gets so big that these atoms the force of gravity starts pushing these atoms closer together than their electrons want them to go. And so in fact you get a situation where these sub-energy levels start getting close to each other and they're pushing on each other. And so the fact that quantum mechanics tells us that an energy level can have only 2 electrons, so one of the things that I certainly never thought to ask when I was in chemistry class, and you maybe never thought to ask, so what the heck happens if you try to put one in? And it doesn't like it. It pushes back. And so that pushing back is what we call electron degeneracy pressure. And so the laws of physics don't want multiple electrons to be in the same energy level. You get 2, that's it. And if you try to put another one in, it pushes back. And so the thing that supports white dwarfs, the thing that keeps white dwarfs from collapsing, is exactly that pushback of the electrons saying, that's it, only 2 electrons per energy level. And so it takes a tremendous amount of pressure to get to the point that is what's driving it. It's not the ordinary pressure. Ordinary pressure comes from just these bonds, which are stable, and they keep you from collapsing more. But if you push past that, then you get this fundamentally quantum mechanical pressure. It's called this degeneracy pressure. And so that's it's an interesting form of pressure, because it has a very different character than other kinds of pressure, which we could talk about. But what Subramanian Chandrasekhar, who was a professor here at Chicago, There's a poster outside about him, I think, right outside of this lecture. He's one of the most famous astrophysicists ever to be in Chicago. And that, if you know anything about the history of Chicago, that's quite a statement. There's a lot of really famous people who are here. What Chandra Sekhar figured out was that, I think he may have been the one who figured out that this degeneracy pressure that was going on in these white dwarfs. And what he said was, okay, so we know that as you make the pressure bigger and bigger, this degeneracy pressure keeps pushing back more and more. So there must be a critical place where if you push it hard enough, that something breaks, where the electrons finally just give up, and whatever, and then we now, and by this time, so we knew we can kind of figure out what happens when they give up, and it's a cataclysm. And so what he calculated was the critical size that these stars have to reach when their gravity gets so big that they beat the electron degeneracy pressure. And that is about 1.4 times the solar mass, so 40% more massive than our sun. And so what happens then is that whenever you go from this each over the special line, and then the electrons give up, and then there's a huge explosion. Whenever this pressure no longer just balances out, but just you have actual nuclear reactions that start going. They're very different. They're pressure-driven nuclear reactions, not heat-driven ones. So it's a very, very weird thing. So you might wonder, how does a star get bigger in time? And so it turns out actually that a lot of stars, a lot of the time, are getting bigger. Because we live in a solar system that has only one star. But a fun fact that I didn't learn until I was in graduate school was that half of all stars are in binaries. And so half of all stars have a friend, a companion star. And so a goodly fraction of stars come in pairs. And so if you have a white dwarf that happens to have a big, fat, gassy star friend near it, then the white dwarf can just suck off the gas right off the edge of the other star. It'd be really cool to see this. This is an artist rendering. We don't have any good pictures of this, but it'd be really great to have one. So the white dwarf is just sucking the gas off. This is what we picture of this companion, and the white dwarf is getting bigger and bigger in time. And so at some point, it sucked off so much gas that it goes over this threshold and explodes. And the fact that it is always the same mass, so the supernovae are always almost exactly the same mass when they explode, is what gives us the hope of having a standard candle. Because you can imagine that if you have a gas cloud, you have the same size gas cloud, and it always explodes in the same way in this electron degeneracy explosion, then you have a hope that they're all going to be the same. Well, they're not all exactly the same, unfortunately. But they're really close. And so this is a bunch of pictures of actual supernovae light curves. It's a little blurry. So I'll try to talk you through it. But basically, this brightness is on the y-axis, and the days. This is one of these funny. So supernovae astronomers, like all astronomers, have bizarre x-axes. And if there's any astronomers in the audience, I apologize, but you have to know it's true. So instead of starting at 0 days would be when the supernova went off, like I would do. What the supernova astronomers say is, well, we're going to say 0 is the day when it's the brightest. And then we have days before brightest, and days after brightest. And I know that this brightest is sort of the time when it's easiest to see, but I still think it's a really funny way of doing it. That's the way they do it. They got the Nobel Prize, not me, so. Anyway, so what we do is you align all the supernovae at the day of, and this is actually probably why. What you end up doing is you align all the supernovae at their brightest moment. And then you see that there are some that are brighter and some that are less bright. What you may also notice, though, is that none of these lines overlap. And so the dimmest supernovae, the ones down here, take less time to get to the brightest and less time to fall off. And the brightest ones take more time from when they explode to get to the brightest and less time and a lot longer to fall off. And so taller curves are also fatter curves. And it turns out what these guys, these Nobel laureates, figured out and calibrated really well is this is a pretty precise law that you can always, if you know how long a supernova takes to rise and fall in its brightness, then you can back calculate using that to figure out how bright it was at its peak brightness, and then you can match them all up. And so if you do that stretching, then you can take all of these different supernovae and stack them all on top of each other. and you get all one curve. And so hence, a standard candle. So then you can look at any particular supernova, use your calibration model, which we calibrate using nearby galaxies. So there's enough galaxies that are close by that we have supernovae and Cepheid variables in the same galaxy. So we use the Cepheids to figure out how far away that galaxy is. And then we can use that information to learn about intrinsically about the supernovae in that galaxy. And then we can use that to figure out what's going on in supernovae in very distant galaxies. And so it's really cool. And people have spent a long time. So they just found that they just figured out, this is one of these just clever things that people come up with. So they just figured this law out purely empirically. No physics at all. They just said, well, gee, if you stretch it by a vector of this much and you kind of push it up by this much, and then you can get them all to stack up on top of each other. And it works really well. And so then we have huge teams of computer simulators who have been toiling away trying to match this empirical relationship. And they're getting close. Supernovae are really hard to calculate in computers, actually. But it turns out that they think, I haven't followed this super closely, but this brightness actually has to do with decay of radioactive nuclei. So the brighter supernovae make more of these, some particular radioactive nuclei. I think it's an excited form of nickel. I can't remember. Does anybody know? Okay, it's a long shot. But and so they make, in this explosion, it turns out that a lot of the light doesn't just go straight from the explosion into light. But a lot of the energy goes into forming radioactive nuclei that then decay into very bright light. And so this decay time then correlates with how intrinsically big the explosion was. That's pretty cool. And so this is a plot. So if you take this information and use these supernovae to figure out the intrinsic distance to a galaxy, and then use the redshift to figure out when this event took place, then you can make a distance versus age plot, and then compare that to your different models of the universe. And what you find, and what these guys found, was that it's easiest to look down here where you subtract out so you can see this overall motion. So you just subtract out that overall motion. And you have basically all the red dots are particular supernovae observations with their errors. And you can plot 3 different cosmological models here. And this is the one that everyone thought before the supernova were observed, which is that the universe is, so basically everyone thought, so these numbers relative to 1, so this tells you if these numbers add up to 1, you have a flat universe. And so this is relative to flatness. So everyone, before the supernova observations in the late 90s, thought that this is where we would live, that we would have a flat universe that was all matter. But you can see that really doesn't match the observation at all. And so the closest you can get is to say, well, what if we have less matter, but so not a flat universe, but also only matter? Then you get this line, which also doesn't match. So it turns out to get a universe that actually matches the data, then you have to put in this omega lambda, omega dark energy. So this is the density, the fraction of the density in dark energy. And then 72, 75%, something like that, you actually match the observations. And so that's how you know. So that's how we first glean from the observations that we are in fact accelerating in our expansion right now. And so just on this plot, just to explain to you, so all of these supernovae up here, all these dots up here, are from billions of years ago. And so it's the comparison of what they were doing with these ones down here, which are from very close by. So we use these close by ones to calibrate this curve, and then we compare this calibration set with the ones from a long time ago, and to figure out what's going on. And so supernovae were the first indication that this was happening, but by now we have a lot more data. And so one of the ways we like to plot this is sort of this funny contour plot. So let me explain it. And so basically on this y-axis is the fraction of the total density in dark energy. And the x-axis is the fraction of the total density in matter. And so then you can say various different kinds of observations can tell you where you're permitted to live on this diagram. And so the supernovae tell you you're permitted to live anywhere in these blue ellipses. And the darker blue ellipses are higher probability. And then it turns out the cosmic microwave background radiation tells us we're permitted to live anywhere in these sort of reddish ellipses. And so, since we know that both the cosmic microwave background radiation and the supernovae are in the same universe, then we better live where they overlap. And so where they overlap is right in this tiny ellipse right here, which is the one that tells us we're at 75% dark energy and 25% matter. And this green curve is one I'm not going to talk about too much, but it comes from doing observations of galaxy surveys. And you see that it matches the other two very well. And so we have now many different, and there are other data sets that agree with this basic story. And so this confluence of many observations has really convinced even the most diehard skeptics, and there were many very diehard skeptics of this, that we are in fact in an accelerating phase. And so there's really no getting around it. And we're just stuck. And so I'm a theorist. I've been talking about observations for this whole talk. And so why do I call this a crisis? What does the theory say? And so in the previous talk, I mentioned that the inferred density of dark energy is a factor of 10 to the 121. That's 10 with 121 zeros after it, more than a Google. That's the mismatch between what our naive theoretical prediction would have been and what the observed value is. So, I mean, basically the theoretical predictions there are two. It was either that it was 0 or that it was this, 121 times what we saw. In both of them, if you have not 0, that's an infinite distance from 0. And this is an almost infinite distance from 0. So you're really messed up. And so that is a really funny number, so I just want to, I hope I won't lose people, don't be scared by the numbers, but I just wanted to give you a sense of why we say this crazy number, 121. And so basically, if you take the dark energy density and write it in terms of like ordinary units, the density of dark energy is 10 to the minus 29 grams per cubic centimeter. It's a really small number. And so if you take that and write it, and so what physicists like to do is to take units like this and write them in terms of one energy scale. And so we basically say, okay, this is basically related to a special energy scale to the fourth power. And so this is theoretical physics voodoo, where you basically say H bar and C are just fundamental constants, so we imagine they're 1 for the purposes of our calculation, and just talk about the energy scale, because that's the thing we can change. We're stuck with these numbers, we can observe those. This is the one we can change. And so if this energy density implies so this density implies an energy scale of 10 to the minus 2 eV. So eV is an electron volt, it's just a really small energy scale. And so what's wrong with an EV? So what's wrong with 1% of an EV as the energy scale of dark energy? So what we do is, so whenever you have a number like this in quantum field theory, then you say, so an EV is 1/100th of an EV. It turns out it's almost exactly the mass that we think is in neutrinos. And so if the only thing that lived in the universe were neutrinos, then this would not be a surprising number. Because if you have quantum effects from neutrinos should give you a background energy density of about this size. And so the mass of the neutrinos to the fourth power is about equal to this. And so, okay, universe with only neutrinos, no problem. But obviously neutrinos are not the only thing in the universe. In fact, they're the by far lightest thing in the universe that has mass. And so to actually do this calculation, to figure out what the contribution of everything else is, you have to put that in too. And so that means, so what's the next lightest thing after neutrinos? Turns out electrons are the next lightest thing. And as we know, electrons are really there, for sure. And so what happens if you try to put electrons in? So basically, the energy density in electrons is 10 to the power 32 bigger than the energy density in neutrinos. And so if you want to do this calculation and estimate what contribution electrons, ordinary old electrons, would have to this energy density, then it's 10 to the power 32 bigger than what the neutrinos would say, and it's 10 to the power 32 bigger than what we actually observe. And so you have to explain this away, you need to find some magic cancellation. It's not just one-to-one cancellation, but it has to be a precise cancellation to 32 decimal places. And that's just for the electron. And so you can keep going. It turns out the next lightest thing after the electron is the muon. It's like an electron, but it's a little bit heavier. And then muon, if you just add the muon in, you get 10 to the 40 times bigger than the observed value. So if all you had in the universe were muons, electrons, and neutrinos, then the cosmological constant problem, then this number would be 10 to the 40. And so the reason we get to 10 to the 121 is that if we put in every energy scale that we know exists, and we do this, all the calculations keep going up, then what we find is that the mismatch between the observed number, 10 to the minus 2, and all the biggest contribution we could imagine is a factor of 10 to the 121. And so that's a big problem. And so what that has led to is, I mean, in some ways this is a theorist's paradise because we can invent lots of ideas to explain this. The problem is that none of them seem to be very good. And so some friends of mine who are experts in this field, trying to categorize all of the different ways people have addressed this problem, made this sort of a spaghetti slide with all these different branchings for none of these are completely ruled out, and so you can just kind of take your branches and talk about different ways that you might construct a theory to explain this strange phenomenon. And I don't want to really spend too much time going through all of these crazy things, but just to show you that, you know, it's not for lack of trying that we haven't explained this. In fact, we're in a situation where you have a lot of ideas and none is clearly right, and that is, for scientists, a crisis because we don't know what to do. Whenever we have lots of ideas and we don't know which one is correct. And so, so I wanted to spend a couple of minutes before we end talking about basically the two sort of like main branches of these ideas. And this is different from the main branches pictured on the slide. Because the slide, which is also on the handouts, is more of a theoretical branching plot. And so this is more of a conceptual branching. And so basically the way that people think about this is basically two ways. One is that you really have just this cosmological constant, this number that we can't explain, that our theoretical prediction is way off on. And there's just, because the theoretical prediction is so off, what a lot of people say is that there's no principle. We've run into an answer that we give up on physics. We give up on principle physics. We don't think that there's some fundamental law that explains this. And instead, this has led people to say is that, it's an accident. It's just an accident that it's this number, and that there's a lot of different universes out there, and every universe just randomly picks one of these numbers. It could be 5 billion, it could be 2, it could be 10 to the minus 2, whatever. Every universe gets its own number. But the interesting thing is that only universes, so one of the things that a famous physicist at the University of Texas named Steven Weinberg pointed out a long time ago, in fact before this number was observed, was that if you have this cosmological constant, if you have this dark energy, it has to be quite small if you want to be able to live in a universe that has it. Why is that? So if you have a really tiny dark energy like we have, and you have a long time for galaxies to get built up and everything before the universe starts accelerating in its expansion. And one of the consequences of accelerating expansion is that you no longer form new galaxies. That whenever the accelerating expansion really takes off, then the relative expansion between galaxies is stronger than the force pulling them together. And so at some point you stop being able to sort of bring things together. And so the larger this dark energy is, the more of this cosmological constant you have, the earlier and earlier this takes place. And so if you make the cosmological constant big enough, and it turns out this is not a whole lot bigger than our current value, if you make it maybe a factor of maybe 5 or 10 bigger, just a little bit bigger, then in a universe that had a factor of 5 or 10 bigger dark energy, then the growth of structure, the growth of large-scale structure would turn off before you make any galaxies. So all you would get is you kind of get some like clumpy gas clouds, and that's it. And dark energy would take over, and that would be the end of that universe, the structure formation of that universe. And so Weinberg's observation has been turned into it's almost a research program now where you just say, well, if you want to have observers like us living in a universe that has dark energy, it better be a small dark energy. Because if you had more dark energy, we wouldn't be there to see it. And so, and people believe me, argue like crazy about whether that's a good scientific principle or not. And it's really, it's hard to know exactly what to say. The fundamental problem with this, from a scientific point of view, I mean, from a philosophical point of view, I don't think there's any fundamental problem with it. From a scientist's point of view, though, is that you have to just kind of stop at that point. You say, it's an accident. And then, I have to go get it, go tend to my garden. To quote Voltaire. And so, as a physicist, you really like there to be some principle, some new law that's telling you this, because then there's something fun to study. And it just happens to be that way. You don't have anything to do. And so for many of us, and it's interesting, there's sort of an age cut from this. A lot of people who are older, like started in their 50s and up, have just sort of resigned themselves and say, it's an anthropic principle. You people should just relax. And all the young people who still want to distinguish themselves are thinking, oh, no. That would be too mean. And so we don't like this. And what we want is there's something to break, or one of the laws, one of the principles that we've already established to be wrong, and there's to be able to replace it with some new principle that would both explain this funny acceleration and also give us new predictions that we could use to tell if that was correct. And so one of the things, and the reason why I have an X before Einstein, because it's so abused in popular science, is that basically I've been talking about this dark energy like it's a substance, like it's a stuff. And so it's this really weird stuff. And so one of the possible resolutions is that maybe the reason why it seems like there's this really weird stuff is because we're trying to steamroll general relativity into describing this. So what if general relativity is just not the right theory to use to describe this phenomenon? And then maybe that it will seem, in some alternate theory, it will seem like the most natural thing in the world to have accelerated expansion at late time. And you won't have to have this weird stuff around. And we do know that such theories exist. And in fact, I'm going to be talking a little bit about some of these ideas in the next couple of lectures. And so there is some hope that maybe this weird, instead of describing this accelerated expansion in terms of a weird stuff, that we can in fact describe it as a new theory of nature and prove that. And so basically, and I should just say the last thing is obviously that it could be that we just haven't thought of the right solution, and that will be proved by something we also haven't thought of yet. So always I like to leave that option open. And so basically our hope is that so that we're still doing observation, because even though we know the universe is accelerating in its expansion today, we actually don't know much about that process. It's very hard to observe. And so people are doing really good observations. And so two easy ways that without any theory we could know right away that the anthropic prediction was not the right one. As one is if somehow we could prove that this, instead of being a perfectly constant in time density, that whatever is the stuff is changing in time. And so we have a big observational program, the Dark Energy Survey, which is being partially run by Chicago and Fermi Lab, is in fact precisely designed to tell whether the dark energy is in fact constant. Or you do some other observation somewhere else, not on the background expansion, but somewhere, anywhere, find a deviation from general relativity, some way that general relativity breaks down. And then we know that something else is going on. So those are our hopes, that we'll find one of these two things. And so just the last one that just wanted to tell you that, so I warned you, this is the last lecture in the sort of like tale of the cosmos up till today. So the next two lectures will be about speculative subjects in cosmology. So the next lecture will be about extra dimensions. And so what happens whenever, what's wrong with 3 plus 1 dimensions? Shouldn't that be good enough for you? I'll explain why it is. I'll try to give a brief account of why it is that people, theoretical physicists, think about the possible existence of extra dimensions beyond the 3 that we know and love. And in the 8th lecture, the lecture after that next one, will be on this new theory of massive gravity. That's a very interesting and very recent modification of. Well, it's a recent modification of gravity that has an old story. So it was originally proposed in 1932, in the late 1930s by cosmology appears, and has recently been constructed. It's a very, very cool story that has happened only in the last couple of years. It's my personal favorite modification of gravity. And so the next 2 weeks I'll be talking about extra dimensions and my personal favorite modification of gravity. So come back here and I'll take questions now. Before I take questions, just to remind everyone that anyone who needs to leave should feel free to go. And I'll take questions. Yes, sir.
Yes, I read an article by Scott, and his theory was that the universe was expanding into a dark energy field that was larger than the universe,
Okay.
which would account for what's going on now. That it could expand, keep expanding, so that get beyond the boundary of the dark energy field, at which point, if the acceleration expansion would stop, or we eventually contract, we eventually get so small we have a big bang.
Right. Yeah.
That we would have, in effect, a kind of a cyclic universe. Is there any, have you heard that?
Oh yeah, no, I know it very well.
Idea?
All goes around pushing that view very hard. And it's an interesting idea. So the basic point, if anyone didn't hear, is that there's a very prominent and brilliant cosmologist at Princeton University, Paul Steinhardt, who actually was one of the inventors of the inflationary cosmology. And so he later repented of his inflationary beliefs and came to believe the universe actually didn't begin with inflation, but with contraction. And that there's a big bang, that at the Big Bang, the universe stopped contracting and exploded again. And that somehow the universe is always going through these cyclic cycles. And there's certainly a nice economy of description in his picture. But the devil is the details for that, and it keeps not quite working. So I know a lot of, and he's really good at finding new ways to make it work. So I don't want to just say that it doesn't work, but every way that so the very first version was very simple, and people were really thought, well, maybe this is really great. It didn't work, and then they made a more complicated version, and it kind of works, but it's really weird, and a lot of people don't find it very compelling just because of the fine theoretical details are a little hard to make mesh. So you have to, in a very brilliant way, he's trying to swept the ugliness. So in the inflationary Lambda-Cenian picture that I've been describing, you have this ugliness is right out in front of you. So you have inflation, we don't know how it started, and we have this dark energy, we don't know what's going on now. The ugliness is like right in front of you. You can sort of like kind of credit on it head on. And what he's found is a very clever way of sort of hiding both of those uglinesses in sort of like these sort of conceptual areas where it's not so easy to see that his theory is also going to have these problems. But I think the general feeling is that every time other people have looked really hard, the same problems that I'm talking about pop up in his model too. But in a way that's a little bit more subtle. And so the fact that it's more subtle there might mean that he's onto something, but it might also mean that he's just a really clever guy who found a really clever way of rewriting the same problem. So. Yes?
This is just an information on Channel 11, PBS Channel 11, this past Wednesday.
Okay.
The new series of NOVA program studies called The Fabric of the Cosmos.
Right.
And Brian is collaborating with it. It shows and explains a lot of these.
Oh yeah, right. So maybe I should just advertise it.
So it's repeated again on Sunday.
Okay. Anybody who wants to watch even more of the stuff? Brian Green and the fancy graphics done by PBS. Tune in. Thanks for mentioning that. That's a really good.
A couple of weeks ago, and I can't remember whether you were talking about inflation or the cosmic expansion. Kind of shocked me by a statement you made that seemed to pull the rug out of what I thought was the most fundamental principle of physics, the conservation of energy.
Right.
I think the statement you made was something to the effect that the principle has no application in gravitational systems.
That's correct.
And this expansion seems to be an illustration of that.
Is
The
the
density stays the same. And so, since I've been thinking about it, I wanted to ask, perhaps there's a more fundamental principle at work, and I'm not sure whether it's philosophical or physics, but it seems to be violating something, which I would call the Julie Andrews principle, which is nothing comes from nothing, nothing ever could. How does physics deal with that?
Well, I mean, so this is...
Excuse me. And secondly, and I think it may be related, but I'm not sure, you said that the current expansion has been going on for 1 billion years or so. But from the lecture, I'm not sure whether that means that before that it was there, but just so small relative to the counteracting force that we can disregard it. Is it that?
Yeah, no, that was the latter. So I'll answer the second question first, and that is the universe has been accelerating its expansion for the last a certain number of billions years. I always forget the exact precise number of billions because it doesn't really matter too much. But since it's about half its current size, it's been accelerating its expansion rate. And so the dark energy stuff has always been around. Presumably, well, we don't really know. The presumption is that it's always been around, and it just then got to be big enough that it started running the show. And so, and so the universe has always been expanding. It's just that up until the universe was half its present size, it was slowing down its expansion rate. So it was expanding but slowing down, and then the dark energy became the dominant form of energy density, and then it started speeding up. So it was slowing down first. So Big Bang, expanding but slowing down, dark energy domination, expanding and speeding up. So with your first question, nothing comes from nothing. So this is why we have 17 billion theories and why we don't know what's going on. Because we don't know the principle to replace. We do know, so the no energy conservation in gravity statement is just, that one's, we know it's true. It has nothing, it's really easy to see it in something like in this case, but it's just, if you have whole universes that have gravity plus other stuff, then there's no way to write down energy conservation. You just can't do it. Because the fundamental problem is that this is related to the fact that there is no intrinsic time measurement in gravity. In general relativity, there's no fundamental way of talking about what time is. The only way you can get time in general relativity is by putting something else in. And so it turns out that time and energy are fundamentally related, so that if energy is only conserved, whatever the system has time translation invariance. That is, if you look at the system now and later, if you can tell the difference between now and later. If you can't tell the difference between now and later, then energy is conserved in that system. And so in the universe, you can manifest a difference, tell the difference between now and later because the universe is expanding. So it's different from what was 5 minutes ago because the universe is expanding in that time. And so that is why we know that energy is not conserved because there's no time translation invariance. Now, so as to a more fundamental principle, one that, just to throw one out there that people do talk about is thermodynamics. And so one of the interesting things you can say is that there really is a cosmological constant. Is that the cosmological constant, in fact, tells you, so one of the funny things about accelerating space-time is that they have a finite causal horizon. And so because of the accelerating expansion, you can only you can only have causal communication over a finite distance, which means there's a finite amount of information content to a universe, to any particular observational patch in the universe. And so it turns out the amount of energy, or the amount of information is also the same number of the mismatch between our prediction for the cosmological constant and the observation. So we know that there would be 10 to the 121 distinct quantum states available possibly in our universe if our observations are right. And so one of the principles that you just say is there's some fundamental amount of information. You can make some kind of information statement because entropy and information are fundamentally linked. And so, entropy being the tendency of things to be disordered. And so, it's possible that and so people like the idea that there's some interrelationship between sort of a fundamental lack of, statement about how much energy a spacetime can contain and the cosmological constant. But to formalize that in a principle, we haven't figured out a really good way of doing it. So that's just a suggestion for a principle that people do talk about.
Could their energy be a function of entropy? As it goes up, it becomes more and more powerful.
So, in a sense, yeah, that we would like to figure out some way of making that happen. Because exactly that as the universe gets older, it becomes more important. But the problem, and in fact, there's this. I'm trying to figure out how to phrase this exactly. The problem is that if the cosmological constant is the way it is, which is just a constant in space and time, not varying anywhere, it's hard to see how you can have particular things like, I'm increasing the entropy now, right? So I just increased entropy by knocking on this table. And so how you feed back that localized source of heat and sound into something that's constant across all space and time basically requires you to posit that information can travel somehow at infinite speed and be transmitted everywhere simultaneously. And so we don't want to give up the principle of finite causation, of causality. So as long as I have to keep causality, the information only goes at the speed of light, and I can't have entropy in local places go to something that's spread evenly through space. That doesn't stop some people from trying to do exactly that. I have a good friend who's a professor at University of Waterloo at the Proto Institute, where I used to be, who has exactly, pretty much precisely tried to come up with a theory that does that. You have, in his theory, you have black holes are very particularly potent forms of sources of entropy, and that somehow the formation of black holes, in fact, turns on cosmological constant. And his theory turns out he can kind of make that part work, but almost everything else breaks. And so to try to come up with a practical theory of that is very hard. It's not a terrible idea, but it has technical difficulties. Yes, sir.
Yeah, I asked this before, but we say that gravitation is a deformation or the reflection of gravitation is a deformation in space.
Right.
You understand that? But then they talk about the force that gravitation or the graviton transmitted force.
Right.
Or which one is it?
Well, I think so you're asking about, so we describe gravitation in two ways. One is the deformation of space, and the other is as the exchange of the force-carrying graviton. And I think the answer I gave you before was the same one I give you now, which is that we don't know how to do that. We don't know how to connect those two pictures. I would love to know how to connect those pictures. That'd be my best chance of getting to following this nice gentleman from the beginning of the talk.
Maybe
Sweeten.
have to do something like light that could be represented as a particle or as a wave.
Right. It's precisely what we'd like as a sort of like as a particle curvature of space duality. Yeah. So we would like to have a picture like that. It's very hard to do that connection. It's just we know that both views are correct. And we use both of them interchangeably. Sometimes one is useful, sometimes the other is useful. But how you do a precise matching between a quantum of gravitation and the deformation of space is just very, very hard. Yes, sir.
So I recall that in 1998, when the accelerating universe was first determined, that the determination was made from type 1a supernova at a distance of about 9-10 billion light years.
Right.
And they extended it so far to 13.7. But we're looking back in time.
That's right.
Doesn't this really mean that our local universe is what is expanding, accelerating and expanding?
Yeah. So when we use that, that's what I was trying to say. Is that that's why I think this comparison between local. We need an anchor point both close by and far away, and it's by comparing those anchors that we can figure out by comparison what's going on now. Because all we look at now is we say we're going, if you suddenly woke up in a car and said, I'm going 60 miles an hour, you won't know if you're slowing down, you're coasting down, or if you sped up from rest. And so in a similar manner, we wake up at the Earth, and we say, oh, we can look around us and say, oh, we're going so fast. And then we need some other anchor point from very far away to give us a comparison point to say, oh, back then it used to be going slower, and now it's going this fast. Oh, we must have accelerated. And that's
So we are accelerating at the greatest speed now.
yeah. So it's the velocity now is the greatest it's been since the Big Bang. So that is much smaller than if this inflationary epoch happened. That acceleration rate was far greater than anything we'll ever achieve in our future, unless something equal. Again, unless something crazy happens. But so yes, you're absolutely right.
But the inflation was not acceleration, was the creation of space.
Right, both. I mean, they kind of go together. So during inflation, the expansion rate also accelerated. Yes, sir.
When you charted the Type 1a supernova, you showed that it didn't follow the constant size of the universe, and it didn't...
Constant matter.
Pardon me?
Constant size of the universe. It didn't track a universe that had only matter.
Okay, and you say it tracked an accelerating universe, and you showed the spots with the error bars. And not that one. Let's see. Go back another couple of... Before that, I think.
Well, there's this one.
No, farther.
Sorry?
No, keep going. I'll let you know.
I think that's it.
Is that it?
Those are all ones I have. On I think this is the one.
Oh, yes, I'm sorry. It's the one at the bottom, right. You said it kind of it tracks the top line, which is almost a straight line, but slightly a curve.
Right.
But it actually looks like a sine wave. It would fit it better than a straight line.
Yeah. So, well, you can try to eyeball something like that. The problem is that, as I think I talked about in the cosmic microwave background lecture, is that we're really good at picking up patterns even without any patterns. And so if you try to put a sine wave in this, it's possible you could find that it would fit better. But then we have a very quantitative game that goes on, which is you have to start putting in new parameters to put in that sine wave. So the question is, as you introduce new parameters to describe your sine wave, does the improvement to the fit justify the addition of all the new parameters? And so with a sine wave, you need two at least: amplitude and a frequency. And that gives you only one amplitude here, or one sine wave. And so presumably this doesn't look like it's like would be I can see it's sort of a bit of an oscillation there. But so if you only get one amplitude and one frequency, though.
Well, if you start from the beginning, it goes up. It gets to the middle, it goes down. Then towards the end, it goes up again.
Right. So it's easy to tell yourself a story like that. So there's a very quantitative series of steps you can do to ask what that happens. And these are the sort of games that we play. You're absolutely, maybe you should have been a theoretical physicist, because that is exactly the sort of fun things that we try to do. We say, let's kind of like a sine wave. Let's see if we put a sine wave in there, what happens. And people do that. It's the easiest. It's relatively easy to throw in a model like this and just see what happens. I'm not sure if someone's done a particular sine wave model for this, but people play with that all the time. It's very hard to make anything that's better, that also preserves this principle of introducing as few parameters as necessary. Because the more complicated you make the function, you can nail every point. You can just make a function that exactly goes through every one of these points. But then you have tons and tons and tons of parameters. And so the amazing thing about this bit that it only has just two numbers. Put in two numbers and you got it. And so it's that interplay that makes it so compelling. But you're right. So it's fun to look for patterns like that. But this is also not the exhaustive supernova data set. And you can look at other data sets. And there's actually many, many more supernovae. So you'd have to fit them all. And so, it actually would be, if you wanted to do it, I would be happy to tell you more or less where you get these data, and how to do it. It's actually relatively straightforward the things to do. People would probably say, if it really did work, people would go, oh, that's kind of cool. You can publish a paper.
I wonder what you thought of the announcement this week that the fine structure constant was observed to be different parts of the universe.
Oh, so that's not a new observation. someone else mentioned it to me. Was it?
Yeah,
You mentioned it. Was it on the radio? What was it? It has not been observed to be. So there are some observations that are suggestive of a non-constant time structure constant, but they're not. It's not like we measure that like we measure the weight of there's some suggestion. There's been this persistent series of observations that seem to suggest that in a certain way, but they're not related to significant ones. But I'll finish asking questions. Sorry.
Well, I just wondered if it's true, what consequences that has to cosmology.
So if it were true, it would basically mean it would violate the principle that we have of homogeneity in isotropy, so that the universe space is uniform. The laws of physics are uniform in space, which would mean that we'd have to introduce non-uniformity in our law. People have thought about how to do that. There's the place I used to be post-object perimeters. There's a whole conference based on people who think about variation of fundamental constants. There's a lot of professional physicists who think about it. I don't find those models I find those models really ugly personally, and I find those observations not to be particularly compelling. It's one of these things where extraordinary claims require extraordinary evidence, and so the accelerating expansions, this is crazy. Everyone thought this was completely nuts, and it took a lot of data before we looked at this. A handful of observations of stars, which is what they've done with these variation of high structure constant, is certainly, it's interesting enough that they give them another grant to keep going on, but until they really nail it, and they remove every possible other source of error, and they've convinced everybody who knows way more than I do about it that they're right, which they have not done, then I am not willing myself to commit to that being true. But there are people who work out the consequences, and to be honest, one of the problems with that particular set of theories is that sometimes you get nice stuff if there's a funny observation, then you get these nice consequences, where it's like, oh, if you have that, then you have this other cool thing. And those, it just seems like they just basically they have to do sort of an ad hoc description and say, we match this observation, and then you're done. And so there's a certain beauty about, all the laws that we found that keep working, tend to have this aesthetic quality. And, you can argue with me about whether aesthetics should be come into selection of physical laws, but for most theoretical physicists, aesthetics do play actually a pretty important role in how we discriminate between theories that are good and theories that are bad. And theories that look ugly, most of us reject because our experience, in historical experiences, of the ugly theories have been the ones that have been ruled out. And the beautiful theories have actually been demonstrated to be true. And that doesn't mean that it will always be true, but for a lot of us, it introduces a prejudice that we should have a bias against ugly theories. And those theories have so far all been ugly, at least the ones I know of. Gravitation would be pulled away and eventually unobservable. So in our universe, what that would mean is that over the course of billions of years, first all of the distant galaxies, and then all the nearby galaxies, and then all but the very closest galaxies would all first get more and more distant and then disappear. And so you'd be stuck with the universe that was a black night sky. Well, not black night sky, because you'd still see our galaxy. I think by the time that happens, actually, all of the stars in the galaxy probably be burned out. So you'd be stuck in a universe that was burnt out, completely black. And if you bump around somehow, you see that there's a bunch of other stuff nearby. It was all really dim and cold. But then there would be nothing in the distance. So it's kind of depressing. Yes, sir.
You may have said it and I missed it. Have we reached the point where no more galaxies are being formed, and how would we know that?
So we think that no more galaxies are currently being formed. The way we know that is severalfold. One is that we don't see any galaxy formation going on now. And so if we look back in time, you can actually see galaxy formation going on. We have gas clouds, there's a whole lot of gas, not many stars. We have a bunch of stars of the kind that we think are the first kind of stars to form in gas clouds. And as you look closer and closer to them later in time, there's fewer and fewer of these. And so sort of empirically, we don't see any galaxies getting made from scratch now. Theoretically speaking, if we study the way that collapse happens in a universe that's undergoing accelerated expansion, we know that in a universe undergoing accelerated expansion, new gas clouds that haven't already collapsed are prevented from just collapsing from scratch. And that would be another line of evidence. does that mean we can sort of like put every nail in the possible coffin of current galaxy formation? No, not necessarily, but it makes it very hard. Another thing to say about it is that by now, the universe had a long time where structure formation was going on. And basically, what we think happened is that virtually all of the matter got collected into halos, into these big blobs of dark matter. And then all the regular matter fell into those halos. And so most of the matter that was sort of had the potency to be a galaxy, became a galaxy already, way back in the past. So there's not a whole lot of gas clouds that are just on the cusp of becoming galaxies that got stopped by dark energy. What the advent of acceleration really stopped is the agglomeration of even bigger and bigger collections of galaxies. And so in the universe without dark energy, big galaxy clusters will slowly get drawn together, and so you get even more and more supermassive agglomerations of matter. And the accelerated expansion turns that process off. So you get a sort of maximum of biggest thing that ever formed, and no bigger thing will ever form. Yes?
Does light energy have mass? And if so, how does it pick up? If it doesn't have mass, how does it pick up mass when it becomes massive?
So light does not have mass. So light is photons and massless. It does carry energy though, and so there are processes whereby light can be like two photons can collide and form matter, and we know in the fundamental physical laws there's no fundamental distinction between energy in the form of matter and energy in the form of radiation. And there's nothing stopping you from taking energy out of radiation and putting it into matter. And so as long as you respect all of the laws that we have, you can freely turn energy from radiation to matter and vice versa.
Is that where the Higgs boson comes in?
So the Higgs boson does play a role in the creation of matter. I don't want to get into the whole story, but the short answer is yes, sort of. But it's a longer answer than that.
Yeah, that last question actually leads into mine. We all learned that you could convert different forms of energy back and forth. Now, can you do that with dark energy? Does anyone have
Yes, and that's actually, that's an interesting, that's a really good question. And we wonder, we don't know. Because we don't know what it is, and so we don't know how to describe it. So we certainly don't have a microscopic theory of it, because to do this matter energy conservation, you have to have a microscopic theory. You have to be able to say, a quantum, an electron hits a dark energy, whatever, and they interact in this way and make some other thing. But with dark energy, we're disagreeing at the very fundamental level about what we don't even know anything to say about it. Certainly not at the small level. So we don't know. There's no evidence from any observations that there's some unknown. So there's dark energies everywhere, but it's very sparse. We don't have any direct observations that we need to invoke some kind of dark energy-ish particles to explain it. We just don't know. It could be, but I don't know. Yeah. Though to gainsay myself slightly, I'm going to have to answer one more question after this. The other time that we had something like dark energy domination was inflation, and that was somewhat different because in the inflationary period we know that it was not exactly constant acceleration, but almost constant acceleration. And during inflation, we definitely had an exchange of energy between the thing that was making the field of the universe accelerate and other kinds of energy. We know that happened. And so, depending on what's causing acceleration today, and there's some theories you absolutely can have, we know that can happen, and other theories you couldn't. But we don't know. So, one other question? Is anyone who hasn't asked a question have a question? Yes, sir.
Zelda was wrote a paper in 1968 where he said that this is before supersymmetry, the number of bosons equal the number of fermions, and the sum of the mass squared of bosons, fermions, and quark powers. You could actually get a small cosmological constant. It doesn't fit any known supersymmetric conviction patterns, but has anybody looked at that?
I'm not aware of it. Sorry. Okay, so I'm going to stop there.